All right, Internet. This is elementary audio tutorial number 1. Today we're going to make a MIDI-enabled polyphonic synthesizer in elementary. And if you have not seen the introductory video, I recommend watching that first because today I'm just going to pick up basically right where I left off with the examples and the slides during the presentation, and just try to build that out into a fully functional synthesizer. So not a lot of context today. We're just going to jump right in and start making stuff, which is more fun anyway. So here we go. Here is the file that we're going to work with today. This is like the hello world of elementary. We've got our require statements. This is elementary core, the library, and when you write the library import, it'll be from an npm package. But here I'm just grabbing the local one because I have some dev stuff in there that I need. This is the path module underneath, just like the normal Node.js path module. And then we've got the load event, and when the load event fires, we're making a sine tone at 440 hertz and multiplying that by 0.2 just to pull the gain down so that when I play it, it's not super loud. And then rendering that in the left and the right channel. So run this, and we've got a sine tone. Cool. So really, I just want to go straight from this to putting it together a synthesizer because I think it's ultimately a pretty small step. So I'm going to take some code from my notes here because it'll save me some time. But right here, what we've got is basically, I showed this in the synth example slide in the presentation, so hopefully this doesn't look too confusing at first. This is basically just setting up some initial state for the synthesizer. So I'm going to use 4 voices, and each voice will have a gate, a frequency, and a key. I'm going to get rid of this note number. We won't need it for this. So the frequency is going to be the frequency that the voice is playing at, and the gate will be basically on or off, 1 or 0, if the voice is active. Each voice also has a unique key, and I will come back to why that's important. So with this, I'm now going to write a really simple synth voice function where, given one of those voices, I'll call it voice for clarity, I'm actually just going to return this thing for now. So it'll be 0.2 times voice.gate, and then l.cycle at voice.freq. So down here, I can now write, our output will be el.add. So I'm going to add the result of mapping each of these voices over synth voice. Right? So as this is right now, we're not going to hear anything because there are no voices active. But for example, if I turn this one on and this one on and put this to 880, we should hear 2 sine tones. Cool. Put those back to default values. So now we're in a place to add the MIDI handling, and this part is really neat. So again, I'm going to copy a little bit of code from my notes because I don't want to get it wrong. Lose a lot of time that way. Okay. So this function is called update voice state, and the goal is that when we receive a MIDI event, we want to update that voices array that I just showed you to basically handle that MIDI event, right? So when we get an event, it should have this type property. Actually, it might not. So if it does have a type, and the type is note on, then we basically grab we grab the next voice from the voices array. We'll set its gate to 1.0, we'll set its frequency to the MIDI event note frequency. We don't need that anymore. And then we'll move that voice index. So we're just gonna set the next voice farther down the line so that on the next event we allocate the next voice in the array, which is really just a simple round robin scheme. If the event type is a note off, then we're going to walk the voices array to find, this is freak, and this is mode frequency, to find that voice who's rendering the frequency that we just let go of, right? If I let go of an A on the keyboard, I want to find that voice that was playing the A and silence that one. Maybe there's a better way to do this, but this will work for our purposes for this video. So we're going to go ahead with that. Now, hopefully that part makes sense. And now all we have to do is wire up actual MIDI handling. So to do that, once we hit this load event, I'm going to put on a new event handler. Really simple. The MIDI event will fire when we get a MIDI event from a connected and active MIDI controller, which I have sitting right next to me. So I'm going to take that event, I'm going to call update voice state. And now I'm going to take this chunk and put it inside here. Okay, so now once we load, we're not going to do anything other than install this handler. Once we get a MIDI event, we'll update the voice state, and then we will recompute kind of the signal flow for all of our voices, and then we'll render that in the left and the right channel. Let's go, let's see it. Yikes. Okay. That's probably a bug, but we're fine. Let's go. Let's go with that. I'll fix that before the beta, don't worry about it. So I'm pushing notes on my MIDI keyboard right now that's connected to my computer. Cool, all right. So really basic MIDI sine tone synth. But we can do a lot more here with just a little bit of code. So the first thing I want to do is I want to explain a detail of what's actually happening right here. And this will kind of explain why that key property is actually important. So notice that, you know, this MIDI event gets called anytime I push a key or let go of a key or something, right? And so I'm making many calls to core.render. And what Elementary is going to do every time you call core.render is it's going to look at the last thing that you asked it to render, and then look at this new thing that you're asking it to render, and figure out how to get from point A to point B, you know, as optimally as possible. And so what's happening here is when we allocate a new voice and we re-render the voices struct, re-render the signal flow based on the updated voice array, Elementary sees the thing that you just asked it to do and the thing you're asking to do it now, and by default, it actually, you know, it sees these things as completely different signal flows. And so when this process takes place, it will basically like completely replace what you're already doing with the new one, which is neat because you can have like smooth graph topology changes and stuff like that, but that's actually not what we want here, right? We want continuity between renders. And so the way to do that is with this key property. So each voice, you'll remember, has this key property up here, and it's unique to the voice. And if you're familiar with React.js, this is a pretty similar concept. During the kind of, you know, two-tree reconcile step, we want to help Elementary find basically the similarities, right? So to do that, we have to make a small change in here. So instead of writing an actual like numeric literal here, I'm going to write el.const. And a const, like if I say this, for example, oops. There we go. Okay. If I write this is identical to what we just had. But the important piece about having the const kind of spelled out this way is that I can pass properties to the const node. And one such property is the key. So now, when we, once I've made this change and we have that, nth render pass, Elementary is able to find that this constant value is the same, like kind of the same one as the last one. And so elementary will see that and identify the similarities here, and then be able to just update the value of the const node without having to kind of, tear anything down and make anything new. So for this to work, we actually have to do the same thing in here. el.const key will be voice.key, value will be voice.frequency. Now, the last detail here is that we can't give both of these const nodes the same key because elementary will think that they are literally the same thing, and we'll have, a super loud gain or something if it uses the frequency value for the gain. So we want to avoid that. So I'm going to just basically tack on a little bit of extra unique identifying stuff. Okay, so if I do this, now during that next render pass, elementary will be able to say oh, the thing that you're asking me to do is basically exactly the same as the last one, so I just need to update these constant values. And if we run this, so same thing, right? But maybe you noticed that time that we're hearing clicks and pops. And the clicks and pops here are a good sign because it means that we're just abruptly turning an existing constant value from 0 to 1. Which is great. That means that we have achieved kind of the optimal step from point A to point B. And now we can keep going basically. And this kind of piece on the render step and keys and similarity and things, this will all be explained in the docs in better detail, but hopefully that's a solid 5-minute introduction to this concept. So now that we have that, checking my notes again, now we get to do the fun stuff, really. So let's fix those clicks and pops to start. And so what I'm going to do here is take this. I'm going to call that constant value of the gate. And then let's make an ADSR envelope. So el.adsr, this is an attack of 4 seconds, decay of 1, sustain at 0.4, 2-second release, and then the ADSR is triggered by the gate. And so when the gate goes high, we trigger the attack phase and the ADS phase. When the gate goes low, we trigger the release phase. So once we have that, I can get rid of this and I'll just multiply the tone by the end. Let's start with that. Oops. Cool. All right, so we've got an end. What else can we do? Well, one of the questions that I've gotten already is kind of speaking to what sort of wave shape options are available. So these are enumerated in the docs, and the docs will be public very soon, as soon as I'm basically ready to announce the public beta. But for short, there's the cycle function, there is a triangle, a square, and a sawtooth, and these are kind of your low-frequency naive oscillators, which you wouldn't really want to use for audio rate stuff. But we've also got some polyblep oscillators, sawtooth, square, and a triangle. So let's just change that cycle to, whoa, I believe it's called blep saw. Same thing, npm start. Cool, all right. That was easy. How about, let me go with, so I'm going to go change that to the synth and then actually, I'm going to leave that as is. So that's cool. Now each voice is a sawtooth with a ADSR curve. And now down here, so we've summed all those up into this output variable, and now I think it'd be neat to filter them. So let's put a super simple, that's 800 hertz cutoff frequency, 1.4 resonance, and then we'll filter that out structure. And this time we're going to render filtered and filtered. Start it. Cool. All right, keep going. This is fun. Here's a little function from my notes that I use all the time when I'm just messing around with elementary stuff. So this function is called modulate, and basically it takes a signal and then it modulates that signal by summing a sine oscillator at the given rate multiplied by the given amount. So we can, for example, modulate that 800, and let's modulate it at, I don't know, 10th of a second, and we'll go 400 hertz. So we'll modulate, basically sweep, this is kind of like applying an LFO to the cutoff frequency, right? We're going to sweep between 400 hertz and 1200 hertz at a rate of 0.1 hertz. Start that. Cool. That sounds nice. Let's just, for fun, see what that's like. Cool. Love it. All right. I don't want to make this video super long. I don't want to make a video where I'm just, you know, in my own zone making noise. So I'll try to keep this structured and wrap up pretty quickly here, but we can still do more. So, for example, let's take that filtered and let's add a delay. So I'm going to, it'll be L.delay. So I'm going to use 44,100 samples of the kind of maximum delay size. And then I'm going to set, there's this function called ms to samps in the library. So this is 500 milliseconds converted to sample time. And then this parameter here is feedback, for which I'll put like 0.6. And then I'm going to delay the filtered signal. So that's cool. But then I want to add the filtered to the delayed. Otherwise, we're only going to hear the delay and the feedback. So I want to hear, like, when I push the note, I want to hear that and then have the delay kind of come in on top. It's kind of like a wet dry right there. So that looks good. Let's render out and out here. So it has. I'll call it wet dry. Cool. All right. Last one, and then I'm going to wrap this up. Let's take, I'm going to grab another one from my notes. Let's take that, well, let's do this. All right, so I'm going to go, let reverb. Now, there's another node here called convolve, so I'm going to convolve the wet dry signal with a big like Hall impulse response that I have in this directory here. This is where the node path library comes in. Wet dry, and now I'm going to do basically wet dry 2. I'm sure I could name these things better, but here we are. All right, let's try this. So we have, one more time from the top, this is the sum of our voices. We are filtering them and modulating that filter cutoff. Then we are delaying that with a little bit of a feedback delay. We're summing that with the filtered signal. So we have kind of a wet dry filter plus delay. Then we're putting that whole thing through a reverb. And then we're kind of wet drying that reverb back with the synth. Save that. NPM start. Sweet. I don't really know what I'm pushing on the keys. I didn't plan any of that, but that's it, I think. There we have, this is 60 lines of code. We've got a 4-voice MIDI-enabled polyphonic synth. We've got a filter with a cutoff, modulation, delays, reverbs, and it only took, I think, 20 minutes. So I think, obviously, this leaves, I'm sure, a lot of room for questions. Please check out that intro video. I'll put a link in the video description as well to join the Discord channel for elementary audio. Ask away, ask any questions you have. I'm happy to answer them. But really what I wanted to show with this is first kind of take that synthesizer example from the first video and really finish it. But then kind of also show at the same time just how much you can do so quickly. I guess for me it's quick because I I know the library in and out. But the documentation will be there, and once you learn the library in and out, it'll be that quick for you too. And look at that, that is a pretty cool project to do in 20 minutes. So I'm super excited about this. I hope that you're excited about this. There will be more videos. I've got some more kind of cool examples that I want to walk you through. And public beta will be announced very soon. Jump into the Discord channel. In the meantime, I'll see you there. Thanks.